In the first lecture on quantum dynamics, we have seen a brief introduction regarding the quantum dynamics. Actually, we have seen that when we consider the time evolution of the state of a system, then actually there are three situations. In fact, in three situations you have seen that either the state vector psi or the Hermitian operator A hat corresponding to an observable may vary with time. In fact, in first situation we have seen that the state vector change with time, but the Hermitian operator A hat does not change with time. In fact, that a physical condition is known as the Schrodinger picture. But when you consider that the operator A hat is time dependent but psi is not time dependent, then it is called actually the Heisenberg picture. And when we consider the time dependence of both of the state vector and the Hermitian operator A hat, that is called interaction picture. In this first lecture on the picture, we are just going to discuss the Schrodinger picture. And so purpose is actually what? The purpose of any picture is, if you know the initial state of a dynamical system, then how we can find its final state. It means if its state is known at a given time, let us say t0, then what will be the state of the system at any other time t. This is the purpose of any dynamical picture. So let us start to discuss the Schrodinger picture in this lecture. As you have seen in Schrodinger picture, the state vector psi, or you may also call it Ket psi, is a function of time. That is, you say that psi is equal to psi of t. But the Hermitian operator, as I have told you, A hat corresponding to the observable A, is not time dependent. It is independent of time. It means A hat is not equal to A hat of t. Since in this picture psi is a function of time, so definitely the equation of motion of the system will be an equation for the state vector psi, not for the operator A hat. Again, according to the postulate of quantum mechanics, you know that if we know the initial state, that is the state, you know the state vector at any initial time, let us say t naught, which is psi t naught, then it is possible to find what will be the state vector at any later time t, that is what will be the value of psi t. It is possible to know. In fact, as you know, this state vector psi is a vector of linear vector space. And since it is a vector of linear vector space, so the relationship between the initial state vector, that is psi t naught, and the state vector at any time t, that is psi t, must be described by a linear operator. And that linear operator you have studied in the mathematical formulation of quantum mechanics earlier, is denoted by this symbol u hat t comma t naught. One thing I would like to share with you, before going to follow this lecture, you must watch the lectures on mathematical foundation of quantum mechanics, which I have discussed earlier, because for a concrete understanding of this Schrodinger picture or any picture, you must have a concrete knowledge of operator formulation of quantum mechanics, particularly the unitary operator. And that unitary operator I have discussed already earlier, so you can remember it. And if you are not remembering, go through the previous lecture on mathematical formulation, particularly unitary operator, and then you will understand these things clearly. Now, as you know, when this operator u hat t and t naught will be operated on the initial state vector, that is psi of t naught. Then you get the state vector for the system at any later time t. So I have mentioned here that psi of t is equal to u hat t t naught equal to psi t t naught. In fact, instead of psi of t, you may also write ket psi, so, but it is not very necessary, so I have not written here ket psi. In fact, this u hat operator is known as the evolution or time development operator. Evolution operator or time development operator, this u hat is known. Now, if you change this t naught in equation 1 by t and t by t1, it means we have to use t instead of t naught and you have to use t1 instead of t. Then what will be this equation? You can see. Instead of t, we will write in fact t1. Instead of t naught, we will write t. So you can see this equation now becomes psi of t1 equal to u hat t1 comma t psi of t. But this psi of t has been defined in this equation 1, and that is equal to this much, u hat t t naught psi t naught. So let us substitute the value of psi of t from this equation 1 here. So you can see instead of this psi of t, I have written this much from the equation 1. So this is u hat t1 comma t u hat t comma t naught psi t naught. But if you write the expression for psi of t1 directly by the use of this evolution operator, so as you have written that psi of t is equal to u of t t naught psi of t naught, so instead of t, if you consider a particular value of t which is t1, then this will be what? Only t will be replaced by t1. So directly we can operate this operator u hat t1 t naught on psi t naught, and then directly we will get psi of t1. So comparing these two results, you can see psi of t1 is defined here and psi of t1 is also defined here, and this psi of t naught is just common. So definitely this operator u hat t1 comma t naught must be equal to the product of the operators u hat t1 t and u hat t t naught. So comparing these two results, we can write u t1 t times u hat t t naught equal to u hat t1 t naught. You can write it. Now, if we will interchange t1 and t in this equation 2, what does it mean? It means instead of t1 you write t, and instead of t you have to write t1. Then what will be our result? You can see here there is t1, so instead of t1 now we will write t, and here is t, so instead of t now let us write t1. Again here is t, so we will write t1, but t naught will remain at age, and in RHS there is t1 which will be replaced by t. So in this way, replacing or interchanging t and t1 in this equation 2, we get this result, you can see. Now let us consider that this t1 is equal to t minus delta t. In fact, here delta t is infinitesimally small. It means t1 and t are very close, and this delta t is very small. So this delta t is infinitesimal, you can say. So in this condition, this result which we have mentioned here can be written like this: u t u t t naught. First of all, I have written that term in RHS. So write this term in RHS, in LHS now. So u hat t t naught equal to u t t1, but t1 has been defined like this. So this is u hat t t minus delta t, and again this t1 will be replaced by t minus delta t. So here will be u hat t minus delta t t naught. You can see from here. Now this u hat t t minus delta t, in fact this is an infinite Samuel unitary operator, and as I have told you that you should go through the lecture on the unitary transformation, where you will see that if this u hat is an infinite Samuel unitary operator, then this is defined like this: u hat t t minus delta t is equal to 1 hat. Actually 1 hat is an unitary operator. The symbol of hat on 1 represents that this is just not mere a number, it is an operator. This is called a unit operator or unitary operator. And from the definition of the infinite Samuel unitary operator, you can write that this u hat t t minus delta t is equal to 1 hat minus I over h bar delta t h hat of t. This is just definition of infinite Samuel unitary operator. So you must remember this. In fact, in this expression, this h hat is what? In fact, this is a Hermitian operator. In fact, you will see sometime later in this lecture that actually this h hat is nothing. This is simply the Hamiltonian operator, or you can say the Hamiltonian of our system. We will see it later on. But for a time being, we do not call it Hamiltonian. We simply call that this h hat is a Hermitian operator. In fact, this h hat is a generator for the infinite Samuel unitary transformation. This is the operator which generates the unitary transformation. So it is called generator of the infinite Samuel unitary transformation. Now let us simplify the equation 3 by the use of equation 4. You can see here. See the equation number 3. In fact, u hat t t naught is equal to u t comma t minus delta t times this much. But u t t minus delta t you have defined here in this equation 4. So let us substitute this definition or this meaning of this infinite Samuel unitary operator which we have defined in equation 4 in equation 3. So instead of this u hat t t minus delta t, we have written here, you can see this much from the equation number 4. And this operator is at each, you can see. Now when you will operate this operator on the operator which is outside of the square bracket, you can see what will be this. This will be 1 hat times this much. Since this is just a unit operator, so this operator will remain same. So this is u hat t minus delta t t naught and minus I over h bar delta t h hat of t and this operator, you can see. Now let us take this term in RHS in LHS. So this will be u hat t minus t naught minus this much, and also divide by this delta t in LHS, or you can say we will divide both sides of this equation by delta t. So in RHS this delta t will cancel out and our result is what? This is minus I by h bar h hat t u hat t minus delta t of t naught. Now as you have seen that this delta t is infinitesimally small, so let us now take the limiting condition when delta t tends to 0. We will impose the limit delta t tends to 0 on this equation. So see this equation and impose the limiting condition delta t tends to 0 on it. So see here, we take limit delta t tends to 0 this much. This is LHS of this equation, you can see here, and we will also impose the same limiting condition on the RHS. Now you have studied the elementary calculus, simple the first principle of differentiation, where you study the meaning of differential coefficient. So what is this LHS? You can see this is nothing, this is simply the differential coefficient of u hat with respect to t. So from the definition of differential coefficient of a function, we can write the LHS of this equation in this way. This is del u hat t t naught by del t. And in RHS you can see, since the limiting condition is delta t tends to 0, so take this delta t here equal to 0. So when we will take delta t 0, our result will be what? This is minus I over h bar h hat of t u hat t t naught. Now this minus sign in the RHS you may impose in LHS, but I have written here I square. It means I square is equal to minus 1. So this minus has been imposed in LHS by taking I square, and so and this h bar has been multiplied in LHS. So this is I square h bar del u by del t equal to I h hat u. Now one of the I, this I and this I square will cancel out, and so this result is I h bar del u by del t h hat times u hat. You can see. Let us say this is equation 5a. Now we will integrate this equation 5 with respect to t between a proper limits of t naught and t. So after integrating this equation, what will be our result? Actually this equation 5 is the differential equation for the state vector, and we also want to find what will be the integral equation for this state vector. So equation 5 is the differential equation for the unitary operator u hat. And now our aim is to find the integral equation for same u hat, and for that we will simply integrate this equation 5 with respect to t between the limits t naught and t. So you can say integrating equation 5 with respect to t between the limits t naught and t. What will be our result? You can see. I have to integrate this equation 5, you can see, with respect to t. So see the equation, and now in another page I am just integrating it. This will be du of, let us change the parameter t to t prime, because the one of the limits is t, so I write here t prime. You can write t, but it will be more convenient to write t prime instead of t, because now t is one of the limits, and limits are t naught and t, and this equal to minus I over h bar. See the equation, I over h bar, this much dt, h hat t, this will be integral t naught to t h hat of t and u hat of t naught. Now t, we will replace t by t prime, comma t naught, and dt prime. You can also write dt. It does not matter that we must write t prime, but since t is now one of the limits, so we change the symbol of the variable or parameter. Now you can see what will be the integral in LHS. You can see easily integral will be u, and when you will put the limits for t prime, this will be u hat t prime comma t naught minus u hat t naught comma t naught, and this will be equal to minus I over h bar integral t naught to t h hat of t u hat of t prime comma t naught dt prime. And can you say what will be the value of this operator? In fact, here both the parameters inside the bracket are same, so you can say what will be its value from this definition of the infinite simul-unitary operator. Since you can see from here, if delta t will be 0, then this operator will become u hat tt, and if delta t is 0, this second term in RHS will be 0. So in that condition you can say that this u hat tt will be simply equal to 1 hat, because this term will be 0. So in this way you can say that since here in argument both of the parameters are same, so its value will be simply 1 hat. Have you understand or not? From that definition of infinite simul-unitary operator, you can say that the value of this operator is nothing. This is simply the unit operator 1 hat. So you can say that this u hat t prime comma t naught minus 1 hat, this is equal to minus I over h bar integral t naught to t h hat of t u hat of t prime t naught dt prime. Now let us take this unit operator in RHS, and then you will see that this u hat of actually here there will be t, not t prime, because our upper limit is t, not t prime. You can see this is t, so this will be also t. Yes. Now see, this is u t naught equal to 1 hat minus I over h bar integral t naught to t h hat of t u hat of t prime comma t naught dt prime, and say this is equation 6. In fact, you can see this equation 6 is nothing. This is simply the integral equation for u hat. So equation 6 is the integral equation for u hat. So you can see equation 6 is the integral equation for u hat, and this equation 5 or 5a is actually the differential equation for u hat, you can say. Now let us apply this equation 5a. This is just an operator equation. You can see in both sides, LHS and RHS, there are operators. No physical quantity is present in this equation 5. So actually this equation 5 is an operator equation. Now let us operate this operator equation on a state vector, let us say psi of t naught, equation 5a. So you can say applying the operator equation 5a to the state vector psi of t naught. When we will apply it, what will be our result? You can see. What is the operator equation defined in 5a? You can see we will operate this operator on psi of t naught, and we will also operate this operator on psi of t naught. So you can see what will be our result. This will be I h bar del u hat t comma t naught del t, and this will be operated on psi of t naught, or you may also write ket psi of t naught. And in RHS you can see the operator is h hat of t times u hat of t comma t naught, and this operator will be again operated on psi of t naught. Now, as you have seen earlier, that this operator u hat when operates on psi of t naught, we get psi of t. You can see it, the first equation, just equation number 1, you can see when we operate the operator u hat t naught on psi of t naught, we get psi of t. So in the light of this equation 1, you can see here that this result may be written as I h bar del psi of t by del t, and this is equal to what? Again see, this operator u hat is operated on psi of t naught, and so this will be psi of t from equation 1, you can see. So this is h hat of t and psi of t. In fact, in ket symbol, if you want to write this equation, so what will be that? In ket symbol, we can write this equation in this manner: I h bar del ket psi of t del t equal to h hat of t ket psi of t, and this is, let us say, equation 7a. You can see actually this is the equation of motion for the state vector psi and actually popularly this equation is known as time dependent Schrodinger equation. Equation 7 or equation 7a, both are same, and this is actually the equation of motion for the state vector psi, and this equation you know is known as Schrodinger time-dependent equation. You have already studied this equation earlier. So this is this is the equation of motion for the state vector psi of t or ket psi of t, and it is known as Schrodinger time-dependent equation. So you can say that in Schrodinger picture, the equation of motion is nothing. Simply the Schrodinger time-dependent equation is the equation of motion. And here you can see there is a time derivative of psi, and as I have told you earlier, that in Schrodinger picture, psi is a function of time, not the operator. So this is the equation of motion. Now, in fact, in coordinate representation, this equation of motion defined in equation 7, you may also write. Here the representation is only temporal, that is only in terms of the parameter time, but we can express this equation in coordinate representation. So in coordinate representation, equation 7 may be written as, this will be written as I h bar del psi of rt. R is for the space coordinate, del t, and this equal to h hat of r comma del comma t. This is for gradient operated on psi of rt. This is actually the coordinate representation of Schrodinger's time-dependent equation, or the equation of motion in Schrodinger picture for the state vector. But there are several situations when this operator h hat, which is a Hermitian operator, and now you call it a Hamiltonian of the system. This h hat is now recognized as Hamiltonian of our system. And there are several situations, or you can say there are several problems when this h is not time dependent, but it is independent of time. So if h does not depend on time, then what will be the state function, or you can say the state vector, you can obtain from the same equation, that is which we have studied earlier, that is this equation 5. From this equation 5 we can then find the state vector at any time t. So you can see, so if h hat is independent of t, then from equation 5, sorry, there is some problem, but now let us, the problem has been removed. H hat is independent of time, then from equation 5 you can see the equation number 5 here. This is your equation 5, and from this equation 5 we can write in this way this equation in this particular manner. you can see this equation 5 now can be written as du hat of t prime t naught by u hat of t prime t naught and integral from t naught to t, and that will be equal to minus I over h bar, and in RHS there is h of t, but now h is independent of time, so we will take it outside of the integral, and u have been taken in LHS, so here there will be only dt dashed, and this is from t naught to t. Now see the LHS, the integral of in LHS will be what? This will be ln of u t prime comma t naught, and limits will be t naught and t, and this is equal to minus I over h bar h hat times t minus t naught. Now put the limit. You can see this will be ln u hat t comma t naught minus ln u hat t naught comma t naught, and this will be equal to minus I over h bar h hat of t minus t naught. Now see, u hat t naught, this is 1, and ln of 1 log 1, this is 0. So this second term in LHS will be 0, and so we have only ln u hat t comma t naught. So you can see this is ln u hat t comma t naught, and second term you have seen that since u hat t naught is 0 and log 1 is u hat t naught is 1 and log 1 is 0, so this is 0, and so log u hat t naught will be equal to this much. This is minus I over h bar h hat times t minus t naught. And so if you want to find the value of u hat t comma t naught, what will be this? This will be e raised to the power minus I over h bar h hat t minus t naught, and say this is your equation 9. This will be equation number 9. So in this condition, when our Hamiltonian or this Hermitian operator h hat is time independent, then this operator u hat is equal to this much. So in this condition, if you want to find the state vector psi at any time t, then what will be that you can easily find out. So as we know, psi of RT, this is equal to what? This is u hat t naught operated on psi of R t naught. You know, you have seen in the first equation. But now this operator has been defined in equation 9. So you can see in the light of this equation 9, we can write that this psi of RT is equal to what? This is e raised to the power minus I h bar h hat t minus t naught psi of r t naught. Psi of r t naught. This is actually the time evolution of the state vector. Now, if we consider that our initial time, that is the reference time t naught to be 0. So if we take t naught equal to 0 and at the same time we also write psi of r0 equal to pi of r. If you write like this, then this equation 10 will be what? Then this equation will be psi of rt equal to e raised to the power minus I over h bar h hat into t and phi of r. Phi of r. And this is actually the time evolution of the state vector. And this equation is actually very useful. Actually, when this phi is expanded in terms of the complete set of eigenvectors of Hermitian operator h hat, then you get the eigenvalue equation, and that eigenvalue equation is nothing, that is simply actually the Schrodinger time-independent equation. So in that condition, you may write h hat, let us consider that our eigenfunction is phi of r, and that will be equal to what? Ei phi I of r. Phi of r. This is actually the eigenvalue or energy eigenvalue, you can say. And this equation is nothing, this is simply the Schrodinger's time-independent equation, STIE, Schrodinger's time-independent equation. So this is all about the Schrodinger picture, but in the next lecture on Schrodinger picture, we will see the expectation value of the operator defined in Schrodinger picture.